In the last video, I showed how we got Doom running in TypeScript types, and I promised 2 long deep dive videos on that, and those are coming, but you can think of this as being like a bonus technical video. There was like a final boss of this project. There was one thing that was way harder than everything else. One of the things I hope to show you all in the technical deep dives is that this wasn't a project that was about some kind of like really super expert knowledge of TypeScript types. Actually, there's really not a lot of like super advanced TypeScript type stuff that goes on, believe it or not. There are some tricky types in there, but there's nothing like altogether that complicated. What it really was like thousands of 8 out of 10 difficulty things, a handful of 9 out of 10 difficulty things, and then there was just this one. This one stood apart. So I had been saying the whole time that I worked on this project that it was really important to have an extremely extensive test suite for every single instruction, testing every edge case I could possibly think of. I even did fuzz testing. I mean, I did everything I could. I have a lot of tests. And the reason is because I knew from the beginning that if it ever did get to the point of being like a million instructions in and there was some fault or it infinite looped, there'd be like no way to figure out why. I would be really stuck. I would be kind of like naked and afraid in the wilderness, trying to like feel my way around. In a lot of other kind of programming, you can rely on your intuition. You kind of can pattern match against problems you've seen in the past to the problem you're experiencing today. But a thing like this doesn't work like that because it's all just zeros and ones, literally. It's just gobbledygook. It's very difficult to kind of look at it and make sense of what's going wrong if there is something going wrong. It sounds kind of funny to say, but the halting problem doesn't actually apply to this particular project. There's ways that I was able to look at it and statically determine that it's infinite looping. And around a million instructions, I realized that it was infinite looping. And you're going to see me kind of explain that. I want to kind of give you a preview of what you're going to see next because I didn't in the very beginning do a fantastic job of explaining what I was trying to figure out. I was still kind of shocked and amazed that I got to the bottom of it. But what I was doing is trying to locate the specific instruction where things went wrong. And it ended up being the case that it was like 200,000 instructions before where I noticed the problem. That was 200,000 instructions before was where the memory corruption actually first occurred. So anyway, a lot more that I could say. I hope you enjoy this. I know that for those of you who are new to Michigan TypeScript, welcome. But this is kind of like how we roll around here. We do kind of technical videos like this fairly often. Some people have asked, what is TypeScript? What are TypeScript types? This is not really the avenue for that. But what I would like you to do is, if you could please, in the comments, link to your favorite TypeScript channel that will help people answer those kind of questions. There's no reason not to spread the good word of, like what TypeScript is all about, but we're really going to be focused here and in the future really on continuing to do what we've been doing all along, which is these kind of wacky things. So I hope you enjoy. Here's the TypeScript and Doom and TypeScript types final boss. That was the most wild, intense debugging experience of my whole career. Never has tracking something down involved so many steps. I fixed it. I found out why it was infinite looping. And the way that I found out is horrific. I'm scared. I'm scared. There's no way this makes it into the video. So I'm going to kind of assume that if anybody watches this, it'll be as some supplemental thing. So what happened was it was infinite looping. This here on the right is what I started with. So I found out it was infinite looping in part because I was doing git diffs of multiple different dumps at various instruction points, and they were exactly the same. Now, they were the same except for the instruction count. It's impossible for the system to have 2 states that are equal unless it's infinite looping, because there must be some counter or incrementer or something somewhere. So that's how I knew it's infinite looping. It went 22 million instructions and I babysat it for 10 days. After this, I broke down and fixed a lot of the tooling, but fixing the tooling, I ran it again, hoping that would make a difference. It didn't make a difference. It was still broken. So there's some instruction somewhere that's doing the wrong thing. So what I did is I eventually figured out where there was a bad memory address happening. So the bad read was, oh, I don't actually, sorry, I'm just curious, skipping ahead. Where is the bad value? So the bad value happens to be at 896,533. But I didn't actually see it until I didn't actually see an effect that caused a problem until 1,663,000. So it took whatever that is, 200,000 instructions for that memory corruption to present a problem. So I had to figure out where it was, somewhere in in the distant past. I have a million instructions. It could be any of one of them. It will be one of them though, probably. And it was. So basically the idea is I found the bad result. I found like where different functions start, thinking like maybe I can kind of like line this up to something and compare values in the stack or locals for a certain execution context. And that didn't really work. So I kept tracing it back to where I first saw. So it loaded -1 from memory. -1 is like all ones. And that's an invalid memory address. So it can't load that value from memory. It can't be there. So the fact that it did that, I can look back then and see like when was the first time that I saw that value in memory and try to understand how it got there in memory. So the bad value, I went backwards. The bad value first appears here in memory. And then it's read. This function 50 has a local called L2. So it's read from there. L2 is set at this point. And so then, okay, where does L2 come from? So it's like L2 comes from L1 at this point. Okay, so now what? You know, like, I don't know. I'm in 900,000 instructions in. F50 is the top level. It's like the main function. It's the top level function. So it's like L1 could have been populated anywhere. I realized that I hold the execution context, so I can figure out like I was like trying to figure out where was F50 L1, where was it set? So I went back to like the beginning. It's not set in the beginning. Okay, great. So we can like bisect our way, sort of. It's not really a bisect because you have to be in a function that had the execution context of F50. But I look back and I found like, okay, it has been set by these points. It hasn't been set by these points. And I kind of like narrowed the window until I found the place where the value was set. The problem is the place where the value was set looked fine. The value where it came from also looked fine. Like nothing looked wrong about what it was. So this whole idea didn't work. But it did get me thinking about something that I wasn't expecting to do right now, which was like, it's knocked around in the back of my head that like, I am comparing the results of my inputs and outputs to the JavaScript WebAssembly runtime. But what if I could control the debugger? And I looked at the Chromium, so the WebAssembly debugger, I'll show it to you. The WebAssembly debugger that Chromium provides that I can use is open source. It's in the Chrome DevTools, this thing. It looks like the JavaScript debugger, but it's WebAssembly. So I thought like, okay, what if I could, this is a stretch, but what if I fork this and like do something to it to get it to spit out the whole state of the program at any given moment and dump all of the stuff? Well, that was really difficult. I spent like 2 hours trying to do that. And it was very, very hard. And I couldn't figure out exactly how to even build it, let alone run it in isolation of Chrome. And there's Chromium stuff. And it was going to be a whole big thing. But while I was learning about that, I found out that you can use the memory inspector to inspect different memory values. So like I can come over here, like let's click on module. And then I'm going to click memory. So you see here, like these are memory addresses. Let's go to like F or like 3FF or something. Oops, 3FF, something like that. F. I don't know, whatever. There are memory, take my word for it, but there are memory addresses here. Like 05555. Anyway, I don't know. but there are memory addresses here and you can read the values. So then I got thinking, like, that's kind of interesting. I know that I have the memory object in the index HTML file that I was creating to run this whole thing. What if instead of instrumenting the dev tools, what if I just make a script that will grab the values and I can make a transformer that will take my TypeScript types. It will spread all the stuff together because there's L1 cache now. It's not just memory anymore. And I'll put it all together. And from there, I can just raw compare all of the memory values because it's like a Venn diagram, right? There's like, what are the memory values that TypeScript has that the Chrome doesn't? What are the values that Chrome has that TypeScript doesn't? Because they should match. And then if they have the same memory address, if they have a populated value at the same memory address, is it different? So there's like those three groups. And from there, I can spit out. So like basically what I did is I made a big nasty thing that will allow me to spit out. Like I pass it this whole string, which is like so long. And then it gives me a value back saying, see, I have it say all clear. So in this particular example, the place where it stopped, they all match. But if there's any differences, see like Chrome not TS different, TS not Chrome. So those are all the values. And then I didn't trust it because I had to write it in JavaScript because it's just in one index HTML file. So this differ is really, really important. And I'm going to go back to, see, I have to switch back and forth to Windows and Linux to do this. But this diffing thing is super critical because what happens is this allows me to match up. If I could figure out where a function was called, I could match up that instruction to a breakpoint in the WebAssembly debugger. And then I could pause at that breakpoint, grab the huge like 5 megabyte long string of all of the memory values, parse it, do the Venn diagram situation, compare it, and tell me pass or fail if they match. So this way, but the problem was, okay, so then there was a problem. The problem was, in order to do this, I need to know when every function gets called. Some functions are called for like literally 5 instructions. Like I wouldn't see it because I only sample. So I'm not actually dumping every single instruction because, well, there would be millions of files, right? It would be terabytes of TypeScript types, hundreds of terabytes of TypeScript types, actually. So I only dump like every 10,000 instructions. So 10,000 instructions, it's like I need to get more granularity than I can print one by one, but I don't because it's impractical to do. I could make tooling that looks at all of those instructions and gives me the instruction count at which a particular function was called. But since I can't do that, the only other option is to do it from TypeScript. So I implemented a memory, a call stack, like a call history situation. So if we go to I'll just look at some random thing here. So let's go down to the bottom. I put it at the very bottom. So like this is call history. So this is showing me what the particular values were at a particular point, or like what the quiet biome. This is showing me whatever. F50 was called at instruction 1. F9, function 9 was called at instruction 3. Function 10 was called at 70. Function 11 was called at 332. Function 4 was called at 369. And then function 9 was called at instruction 896,000. We went from 369 to 896,380. So it's like, and I have no idea what would have been called in between there, but it happens to be nothing because I think I'm pretty sure that F4 is just malloc. So that's a routine where it's like adding a lot of memory values. All right. So this method is very important because this allows me to map back function calls, like when a function was actually first called, because this is done from TypeScript. So I map back the value that it was first called, and then I can get a list. So that's what this list here is on the left. So now I have all the pieces that I need, and this was enough to get going, right? I have the functions that and when they were called, and I have the instruction count in my TypeScript side that they were called. And I can map those values just by reading the WebAssembly, by reading it kind of raw. I can look at the WebAssembly code, and it seems like it sounds like something that would be very hard to do, but it's not actually that difficult. Like you can see all these breakpoints. You can see where something kind of first was called. So like F50 is the first function that's called. It's called on instruction 3. So entry comes in and then it puts one number on the stack, and then it calls F50 right away. Okay. So like you can see here, F50 calls F9, then it calls F4, then a little later it calls F9 again, then a little later it calls F9 a third time, then it calls F0, F2, F0, F9, and then it calls F5, but this part where it calls F5 is in a loop. And if we compare that, I wish I could show them side by side, but if we compare that to what I have over here in Notepad, oops, where is it? If we compare that to what I have over here in Notepad, then you can see it's what I just said, F9, and then actually this goes deeper, right? F9 actually calls F10 and F11 inside of F9. But then we come back out to F50, so then we have F4, F9, and then it calls F10, but it didn't this time call F11. I don't know if that's like that's not actually where the problem is. Oh yeah, actually it is where the problem is, because that's between where the failure happened. I found out later. But anyway, the point is, F9, and then 10, 11, F0, 1, 2, 0, 1, F9, F10, F11, and then I told you it calls F5 in a loop. So here it is calling F5 in a loop. This here is the reason why doing this is not practical. And then it comes out of the loop and calls F19 and F15 and F5 and F18, F13. This is the reason why I can't. This is like a debug mode thing. So I added some instrumentation to the TypeScript stuff that I can turn off with a Boolean that will just not log any of this stuff. But this is very important. In fact, I wanted to put more information in here, but this ended up being enough. I wanted to also put where it was returning to. So it's like, you can't see from this level, like, is F10 called by F50 or is F10 called by F9? You can just tell that F10 is called after F9, but actually F10 is called by F9, F11 is called by F9, and then we come back up and F4 is called by F50. So there's like a bit of a tree, and it jumps up and jumps down and jumps up and jumps down a little bit. And you can't see that from this level, but I figured it out anyway. Okay, so I have those values. I map them back to breakpoints, and then at those breakpoints, I can, let's see. At those breakpoints, I can stop and I can compare the values. Now, I didn't talk about this part, but like part of the work of doing all of this was to like go render all of those values. So I have like 2,000 files here of like step-by-step renderings of each instruction. So here's 896515. Here's 896516, 896517. So what I did is, and this ended up being really critical that I took time to fix the debugging and infrastructure tooling, because I used this so much. Because what I can do now that I couldn't do before is I could say, hey, do this like 1,000, like start here and go 1,000 and dump 1,000 instructions at a time. Now start here and dump 100 instructions at a time. And now start here and dump one at a time. And through that method, I was able to kind of like get big chunks and then break them down into smaller pieces until I had the exact things that I needed. And then what I have to do then is, like, let's say we had this one, for example, that we were comparing. So I have to collapse, I have to fold instructions, fold active branches, fold. So this is the L1 cache that was implemented before, and the memory. So I grab all of this. So this is, like, you can see here, 87,000 lines of stuff to my clipboard. I grab all of that and I paste it in Chrome with that check function that I made. And there it does, like I said, the Venn diagram thing, and shows me what values are different and where and how. By doing that, I'm able to incrementally, so like I first did this value and it passed, and I was like, okay, it passed, but like maybe my script is wrong. I'm not really sure that it works. Then I came down here to the bottom and it failed. And I was so excited because look at that range. It's only, that's less than 100,000 instructions. So I got it down to less than 100,000 instructions. It's very exciting. From there, I just kept doing it. I did it here, fail. I took a leap and I did it here and it failed. And I did it here and it passed. Actually, I couldn't, F10 is called within F9. So F10, you can see, is called up here. So I had to put a breakpoint there, jump to it the second time, because I know that it's only the second time that F10 was called. And then I could see that it passed. That means for sure, the error occurred on the second call of F10 between instruction 896,447 and instruction 896,781. That's 300 instructions. I was so happy when I found this out because I will happily sit here and just do like one at a time, like increment Chrome, increment my TypeScript thing, increment Chrome, increment my TypeScript thing, and each time check to make sure that the values are all exactly the same. And I did that. And what I found was there was one place where there was one instruction that did the wrong thing. Imagine that. And that instruction, let's find it here. Is it memory grow? Well, in any case, I have it open in the debugger, I think. That instruction was after, was in F10. Let's call func 0. Okay. So that instruction was in here. So it's funny, like it just doesn't, now that I it's always like this kind of thing, like when you know what it is, and then you can, it's very obvious when you know. So what happened was it's a memory instruction. God, let me find it. Oh, I have to step into F10. Sorry, I'm looking at the body of F9 actually. So what happened is inside of a loop, there's only like 3 times in the entire source code that this instruction is called. It's a kind of a rare instruction, but I guess a very important one. So the instruction, man, I could just search for it and I would find it faster probably. Here it is. So memory.size. What memory.size says is when you call that, when you call that instruction, it will take the number of pages that this has for memory. There are 64 kilobytes in a page or something like that. So it'll take that number. So 64 kilobytes divided by the page size, number of pages divided by the page size. So there might be like 6 pages. So it starts up actually with 6 pages of memory. Then what happens is it pushes that value to the stack. I had done that part right. What I didn't do right was that a little bit down here, there's a memory.grow. What memory.grow does, let's see if we can get right up to it. Yeah, I could have just pushed debug twice and it would have gotten me there. Okay, what memory.grow does, so right now we haven't done it. Now I'm gonna do that instruction. It gives me back the value 9. I, in my code, had the value 8. And I didn't push anything to the stack. The reason I didn't push anything to the stack is because when I originally implemented memory, it was infinite. And so I looked, this is the fix. We're almost to the end here, believe it or not. This has been days of debugging. So what I originally did, yeah, like you're going to see the test case here here. Let's see if we can see it all on the screen at once here. Okay. Sort of. So what I did was memory grow was a no-op. And the reason it was a no-op is because I don't actually have a linear memory. So WebAssembly has linear memory, meaning you have like an array, and the array is of a fixed size. And if you want to insert a memory location, you just change that index in the array. You don't actually like have to go to it. It's not a table, it's an array. So it's linear memory. So I don't do that because I just have an object, and TypeScript doesn't know that this is a memory object. It just knows that it's an object with some strings, keys, and some string values. It doesn't care what's on either side, if the values are reasonable or not. And actually, that's the thing that I saw. I saw that it was setting to a memory address that was like, negative, to a negative memory address, which like doesn't make sense. But TypeScript doesn't care. It doesn't check that, right? It's not a part of the semantics. I could have done that, but I didn't. Anyway, so I looked at memory grow and I thought, okay, I don't need to care. Like this is the original implementation that I had. This was the bug. I just made it a no-op because I'm like, well, I don't care about like growing memory is not, it's not urbane. It doesn't matter to me what I do. But if you look at the spec, there's something a little tricky here. The spec, okay, I mean, if you haven't seen this kind of stuff before, it might be kind of scary, but let me just try to go through it. So what it says is, this is a not responsive page. So let's see if we can do this. Okay, memory size. So this is the memory size one. It pushes a value to the stack. Okay. So we don't care about anything that's an assert line because that's a validation thing and it's done by the parser. So, okay, current frame, this is the memory. So this is the number. A is the number of the size of memory, not in bytes, right? Because we're going to divide later. And then mem, so then SZ, the SZ is the next thing that's important, is the size of the bytes divided by the page size. The page size is 64,000. So the number of bytes divided by 64,000, that's your page size. That's the value of SZ. Then it says pop the value I32 const n from the stack. So you can pass a parameter to memory grow. I didn't know that. And I didn't care because like, I don't care how many pages it says to grow by because we can grow by as many as we need to. There's no limit. It's unlimited memory. And actually it's funny. It says down here, a note about that memory.grow is non-deterministic because depending on the place you run it, it could give a different result. If there's like whether or not the runtime is the thing that actually says whether or not you can have enough memory. And if you can't, then it'll jump in here and return an error value. But I don't need to care about that. I don't care. When I first originally read this, I was like, oh, well, pop from the stack, push the value to the stack. This doesn't do anything. It doesn't matter. It doesn't matter. It takes a value from the stack. It does some shit with the runtime, and then it pushes that same value back. It pushes, if you have 42 pages, when you execute a memory.grow instruction, it will take 42 off of the stack, do something, and put 42 back on the stack. Sound like a no-op to you? It sounds like a no-op to me. And it does do that. But there's something else it also does. It also increments the memory size by the number that was originally on the stack. Well, if you had a memory grow, so let's look at my test case. So this is a WebAssembly instruction just above my head here. If you have a memory size, it will push the number. So, okay, I started this WebAssembly module with 42 pages of memory. So 42 times 64,000, that's how many bytes of memory this module will have. By calling memory size, I'm pushing 42 to the stack. Then I can push another value, because remember, this takes a parameter. I push another value to the stack. So I push 27, it's just a random number. It has nothing to do with anything. And so then I push 27, some random number to the stack. And then I call memory.grow. Memory.grow will, it's almost like it changes this value at runtime, right? It's going to change this value. It's going to increment it by 27, which is this number. So, but there's no like artifact. There's no like way you can see that memory.grow was called other than by keeping track of it in the runtime. And actually, I do keep track of it into runtime. I need to, because if memory.size is called, I return that value. But what I missed is memory.grow has a side effect of also changing that bookkeeping value of the memory size, so that if you call memory.size again later, you'll now get the new value since the last time memory.grow was called. And now we arrive at the fix. So this is the fix. I mean, I think the fix is like, very simple as far as these things go. They're much more complicated state transitions in this project. So basically, I take in the memory grow instruction. I don't need it. There's no parameters for it. The parameter is on the stack, right? It's like but there's nothing specific about memory grow. It doesn't have an offset or anything like that. Okay. So then I grab values off the stack. So I grab grow by, which in this case is going to be like this 27. And then I set the stack to the remaining values. So I'm not touching all the rest of the values. And I'm also I'm pushing a value to the stack of the previous size, which is weird. I don't know why it does that. It pushes a stack for the previous size. Push SZ to the stack. So, yeah, if it succeeds, it pushes the previous. I have no idea why that is. It would make sense to me that you push, like if it succeeds, you push the value that it succeeded with, but whatever, it does what it does. That's the spec. And then I also update that value. So grow by is just a WASM value. It's like, 1 or 5 or 6 or 27 or whatever. And then I come down here and I have a state modifier that will just set this value, and it will add binary to the memory size. So it'll take the existing memory size and it will add grow by to it, updating the value. That's it. That's the whole fix. That's all that was wrong. And that was enough to cause a failure setting at an invalid memory address 200,000 instructions later. And now I have a test covering it. I didn't have a test covering it because it's not a regular. This is a really weird instruction in the hundreds of thousands of different well, there's not 100,000 different instructions, but in the hundreds of different instructions that are implemented, almost all of them are like I32 dot greater than, shift left, I64 load. Like they're methods on data types. Memory, there's only like 3 instructions that are not like that. Memory size, memory grow. There might be like one other, but they're weird instructions. They don't come up a lot. So I didn't have test coverage for this. I think it's the only thing that I've been thinking now, what else didn't I cover? But that's it. It's done. It's ready to go again. I have all the instrumentation ready. So what's cool is that I can also now run this unattended. So I used to have to babysit and like sit down and restart it and point it to the new place to go and just like do all this stuff every 6 hours. But now I just press play and it will go as fast as it can. And then maybe sometime later it will come back. So yeah, that's the sitch. That's the situation. And I can't believe it. I can't believe I found this. This was by such a stretch. This was the most intense debugging journey that I have ever been on. And I said a lot of times, I'm probably going to say to something in this video that I cannot debug this. That if it comes to the point of it gets a million instructions in and it fails on something, I almost definitely will not be able to figure out why. And that's not true anymore. Because I have a way to compare the total memory state with from both runtimes at a given breakpoint, and I can figure out where the breakpoints need to go. Like I can map them back to a function call. That's it. That's game over. There's no way this project can fail now. I just can't think of one. And maybe it would be a performance thing. So I did find out I was very uncomfortable to learn that the memory grows up to like 200 kilobytes from 80 or 90. And that's quite a lot. It's going to be very, very slow. Like it might be, I don't know how slow, but it's going to be very, very slow. So I might need to do something about that. I don't know what I'll do about that, but I'll do something. It can't be worse than this. This is the pinnacle of this project. I really think like there's no way something can be harder than this, because now I have all the tools. It can't be harder than this again, because now I have a way to bisect my way and figure out where the memory corruption came from, And that power is invincibility at this point. So anyway, I kind of doubt anybody will ever see this. I think I'll probably just like put up some unlisted video, and like people are really just can't get enough of this project, then they can hear about it. But this is the craziest debugging thing of my whole career by a lot. I can't even think of a second place of something that, I mean, I used to do Kubernetes development like in Kubernetes. It was not this hard. I can't believe that I figured this out. All right, let's run it again.